In this lecture, I want to talk about how to introduce derived rules into our system, as well as prove and introduce a couple of rules that turn out to be extraordinarily useful, rules that pertain to conditionals. I call these rules for material conditionals. Why I'm calling them rules for material conditionals will probably become more evident when we discuss the nature of conditionals later on in the course. So let's go ahead and start by looking at this sequent. Now you'll note that in this sequent there is a symbol that you've never seen before. That's this double turnstile symbol. So it looks like two turnstiles side by side, except one of the turnstiles is pointing in the wrong direction. Well, what that indicates is that we are to regard this argument as valid in both directions. That is, we are to regard this argument as valid if we take what occurs on the left as a premise and what occurs on the right as a conclusion, and vice versa. So to prove this sequent with a double turnstile, we really need to prove that this argument holds in both directions. So let's go ahead and work on the left to right direction. So here's a good way to get started in proving the left to right direction. Of course, we write down our premise, and it's a good idea to go ahead and try to do this proof by way of reductio ad absurdum. So I will assume the negation of what I'm trying to prove. Unfortunately, at this point though, our rules of thumb don't really give us many suggestions about what to do next. So here's a hint concerning what to do next. It's a good idea to go ahead and assume P. Okay, this should get you started on completing this proof. I will assign the actual completion of this proof to you as a homework assignment. Alright, so now that we have looked at the left to right direction, let's look at the right to left direction. Again, I'll allow you to prove the right to left direction as a homework assignment. Here's a hint. Go ahead and try to prove it by way of OR elimination. Okay, so now that we have proven those sequence, or will have proven those sequence once you complete your homework, let's see what we can do with them. So I want to introduce a new rule, the rule of sequent introduction. This rule is actually pretty complicated when stated, but pretty easy when you see it applied. So let me go ahead and state it. It's a mouthful, and I think though that you'll understand it much better when you see it applied. So here it is stated. If one has already proven that a certain conclusion C follows from certain premises A1, A2 through AN, and one has each of A1, A2 through AN on distinct lines of one's proof, or one has substitution instances of A1, A2 through AN on distinct lines of one's proof that result from uniformly replacing the same propositional variables throughout all of those sentences, one may infer C from those lines or the corresponding substitution instance of C. Again, that's a mouthful. Instead of trying to parse that, let's just look at how the rule is applied. So here's an example. I want to prove this other double sequent, RMC2. And again, since it's a double turnstile sequent, I need to try to prove it in both directions. So let's work on the left to right direction. Okay, so I'll begin first off by noting that a substitution instance for the already proven sequent if P then Q double turnstile not P or Q is the following: if not P then Q double turnstile not P or Q. So I got the second of these sequence from the first just by taking all the occurrences of P in the first sequent and uniformly replacing them with occurrences of not P. Okay, so keep this in mind. Now I'll begin to write out my proof. So I start out by writing down my premise. Now I'm going to go ahead and introduce another line that I'm going to get by way of Sequent introduction. So I note that I've already proven that it follows from if P then Q that not P or Q. And since if not P then Q, therefore not P or Q is a substitution instance of the sequent I've already proven, I may, from line 1, which is if not P then Q, infer line 2, which is not P or Q. I get that from line 1 by way of sequent introduction, by way of RMC1, which is the sequent that I have already proven, and in this case I use a substitution instance of that sequent. Okay, so pause here for a moment, look carefully at what I've done, make sure you understand why I'm able to use the sequent I've already proved to get line 2 from line 1. Pause the video and reflect on it if you don't see it. Once you do see it though, you see that we're now in a position to go ahead and prove our conclusion via OR elimination. So I want to prove our conclusion via OR elimination using the disjunction that I have on line 2. So first I want a conditional that has not P as its antecedent and my conclusion as its consequent. Then I'll want a conditional that has Q as its antecedent and my conclusion as its consequent. So I'll start by trying to prove the first of those conditionals. So I'll assume not P on line 3 and try to get my conclusion. So my conclusion is P or Q, and I note that I can get that by first getting P via double negation applied to line 3, and then once I have P I can use OR introduction to get P or Q. And now that I've got my conclusion, I can go ahead and discharge the assumption that I made on line 3 to get if not P then P or Q, and that's one of the conditionals that I need for my OR elimination proof. So now I'll start working on the other conditional that I need. So I'll go ahead and assume Q and try to get my conclusion. Well, it's really easy to get my conclusion P or Q from Q. I just need to use OR introduction. So now I've got my conclusion following from Q. I use conditional proof to discharge my assumption. So now I have a disjunction on line 2, a conditional that has one of the disjunctions as its antecedent and my conclusion as its consequent on line 6, and a conditional that has the other disjunct as its antecedent and my conclusion as its consequent on line 9. So that puts me in a position to infer my conclusion via OR elimination from lines 2, 6, and 9. And now I am done with my proof. Okay, let's go ahead and look at the right to left direction. So note again that a substitution instance for the already proven sequent if P then Q double turn style not P or Q is if not P then Q double turn style not P or Q. Again, we get that by uniformly replacing P in the original sequent with not P throughout. Your task is to prove this sequent by first proving not P or Q and then using sequent introduction to employ RMC1. So this task has been assigned to you in your homework. and I'll leave it to you to complete it. Okay, well, these rules that we've just introduced, these rules for material conditionals that we have derived and can employ via the rule of sequent introduction, turn out to be extraordinarily useful. So I want to show you just how useful these rules can be. So remember the bonus problem on the Reductio ad absurdum worksheet. Here is the ridiculously long proof that we did when we did that bonus problem. Okay, well, the rules that we've just introduced allow us to greatly shorten that proof. So here is that bonus problem again. Here's a trick. Note that a substitution instance of the already proven RMC1, that is, if P then Q, double turnstile not P or Q, is if P then not Q, double turnstile not P or not Q. I get the second sequent just by uniformly replacing Q with not Q throughout. So given RMC1, I can prove this disjunction, that's my conclusion, namely not P or not Q. I can prove that by proving if P, then not Q. So let's go ahead and try to prove this sequent in that way. So I'll make it my intermediate goal to prove if P, then not Q. And then I'll use sequent introduction applied to RMC1 to get my disjunction not P or not Q. Okay, so here we go. I write down my premise. My intermediate goal is to prove if P, then not Q. My rule of thumb for proving conditionals tells me to assume the antecedent and try to get the consequent. So I'll assume P and then try to get Q. It's not clear exactly what I ought to do next, and when it's not clear what I ought to do next, it's typically a good idea to go ahead and try a proof by way of reductio ad absurdum. So I'm going to try that. I'm going to assume Q on line 3 and try to derive a contradiction. And now I actually see I'm really close to having a contradiction because I can apply AND introduction to lines 2 and 3 to get P and Q. And then that gives me a contradiction with line 1. So I apply AND introduction to lines 1 and 4 to get a contradiction on line 5. Okay, now I go ahead and discharge the assumption that I made for reductio on line 3. Now I have a conditional with what I assumed on line 3 as its antecedent and a contradiction as its consequent. So that puts me in a position to get not Q via reductio ad absurdum applied to line 6. Okay, so now that I've got not Q, I've accomplished my subsidiary goal of proving the consequent of my conditional. So now I back up and prove my conditional via conditional proof. Now I've got the conditional that I was trying to prove, so I've accomplished my intermediate goal of proving that conditional. And now I use the rule of sequent introduction and RMC1 to move from that conditional to the disjunction that I'm trying to prove. So I use RMC1 to move from if P then not Q to not P or not Q. And now I'm done. I have completed my proof. Note how short this proof is in comparison with this one. This is manageable. This is kind of ridiculous. And what allowed us to greatly simplify our proof was the rule of sequent introduction and our derived rule RMC1.